All right, everyone, welcome to the second part of lecture today. It's a real great pleasure to have Ilya Sutskever as a guest lecturer. Ilya was actually behind the result in 2012 that put deep learning on the map from something that looked promising to some people and had a lot of people thinking it's never going to work to actually working and having a massive breakthrough in image recognition on the ImageNet competition. From there was still a lot of people saying this is never going to work. It's just for image recognition. But then next, Ilya showed it for sequence modeling for language, where a lot of people thought language is so different, never can work. It's only for signal processing. He got it working for machine translation and built a foundation of what later became the new version of Google Translate. From there, Ilya built also a language model to generate text automatically. Then he came from Google, founded OpenAI in December 2015. Well, about 3 years ago, and from there, a lot of breakthroughs in all areas of AI within deep learning, reinforcement learning, unsupervised learning, and today he'll tell us a bit about some of the latest results in language modeling, I think.
Yeah.
Please join me in welcoming Ilya.
All right, thanks for the introduction, Peter. Okay, let's start. So, before diving into unsupervised learning and generative models, I want to tell you a little bit about the work we've done at OpenAI in reinforcement learning. And I'll just show you. So, the project we are really proud of is OpenAI 5. It was a pretty large neural network that played a large number of games against itself, against a version of itself, and it became so good that it was able to play on par with some of the strongest teams in the world. And I'm going to show you a brief video of the bot playing against some of the best humans at TI. And so the background audio is going to be, you will hear the casters saying what they feel. The game is pretty hard to understand if you've never played it before, but the emotions of the casters should be easy to understand. So I'll just play the video to you and just pay attention to the sounds.
Oh, no! You can hear it from here. Yeah, and no, that's gonna be fine, but yet another death that OpenAI takes.
Wait, these are your professional players. They do this for a living. That's just, wow, I'm so sorry.
Don't say that, OpenAI.
Oh, come on.
GLaDOS, we're doing well, and yeah, here comes the...
Did it do the maths?
Yeah.
Did it do the maths? OpenAI.
It's beyond math. You don't understand.
So that's what I wanted you to hear. And we will have our final match against the world's strongest team, OG, on April 13, where we will showcase new capabilities. Now, one of the imperfections of OpenAI 5 is that we used very large-scale reinforcement learning, which meant that we needed to consume many thousands of years of gameplay worth of experience. And you could object, you could point out correctly that if you need so much experience, then reinforcement learning is probably not particularly useful for anything in the real world. So we anticipated this concern and did this, which is Dactyl, which is also pretty large-scale reinforcement learning agent, not as large-scale as OpenAI 5, trained in simulation to solve this task, which is reorienting the block. But it was trained with domain randomization, which is a very simple technique where you ask your policy to be robust when you vary various parameters, like the friction of things, for example, which you don't know in your simulator. And if you do this, it becomes robust and it transfers to the real world. And perhaps the bigger point of these results, what should be the takeaway from these results, from the dactyl result with the robot hand or from OpenAI 5. What is the takeaway? The takeaway that I like the most is that the story of deep learning, which has already happened in supervised learning, it has happened with convolutional neural networks, it has happened with LSTMs. The story that the reason deep learning didn't work was fundamentally because the neural nets were too small. When the convolutional neural nets were too small, they didn't work. What can you do with a convolutional neural net with 40 neurons? Not much. Then when you make it large, suddenly it does work. That's been the case with every aspect of supervised learning. And what our results show is the same holds true for RL. In other words, very simple reinforcement learning algorithms, policy gradients based, tactocratic based, turns out they can perform extremely well. They turn into very formidable tools for solving hard problems if you scale them up, if you run them at scale. And to get a sense of it, just try to rewind back to 2016 when people were just starting to solve Atari, and see if you could imagine that exactly the same algorithms with almost no change would be able to solve games like this. I think it was pretty hard to imagine. So that's good. It means that the story of deep learning, that you had this simple idea, previously it was convolutional neural networks, was LSTMs, now it is policy gradients with appropriate variance reduction. If only you scale it up significantly, you suddenly become capable of solving hard problems. And what I want to show you in this presentation, in this talk, is that it is possible that something similar is happening with unsupervised learning as well. And I will give you the evidence. Oh yeah, but before going into unsupervised learning, I just want to show you one video of a research result we did in 2018, which I really like, where we asked a reinforcement learning agent to maximize a curiosity objective where it tries to avoid boredom. And we trained it, and it learned to do this, what you're seeing here. And the cool thing about it is that it's you see that it's not going after the coins because it doesn't know that money is interesting in the game. It just likes not to die. It likes to move forward, because anytime it dies, it goes back to a place where it already knows what's going to happen, so that's boring for it. So it doesn't like to die. Anyway, it keeps going like this for a while, and it's pretty good, and I think it goes all the way for 12 levels or something like this. I'm not sure. It's not clear why it dies. I think if we did it again, it would be even better. Oh yeah, it's going to defeat the boss now, so that's cool. And again, all this happened just because it didn't want to be bored. That's it. Okay, now unsupervised learning. I will tell you why it may be that unsupervised learning is actually pretty straightforward, provided you can train large models. So I will tell you the high-level picture. Why are we seeing unsupervised learning working now? And when I say unsupervised learning, in this case, I will be referring to unsupervised learning for language. Unsupervised learning for images creates a, well, I will go into those details a bit later. But right now, when I say unsupervised learning, I mean unsupervised learning for language. What's new? The big answer is the thing that's new is better architectures and much more compute. So I want to tell you a little bit about why, how to think about unsupervised learning, or perhaps one more way of thinking about unsupervised learning, and why what we are doing ought to succeed. So I want to tell you one idea, which is if you predict the next word really, really well over long contexts, then you probably understand a whole lot about language. That's the core claim. This is not a mathematical proof, but it's a claim. Now I will try to defend it a little bit. Let's say you are reading a murder mystery, and at some point there will be a place in the book which says, okay, it tells you something, and at some point it reveals the name of the murderer. Well, this is training data. You know, if your model can predict that, it means that it's understanding the novel pretty well. Or let's say you are reading a math textbook, and you're trying to prove a theorem, and you can maybe write the first paragraph, but then you don't know how to continue it. Well, if your model can predict how to continue that, then it probably understands the math as well. So you can see that intuitively, it makes sense that if a model, a neural network, can predict the next word really well, then it probably understands language. Now, we are not sure, because such models have never been built before, but it seems conceivable. It's not as good as the kind of guarantees we have with supervised learning, where you just, here's your cost function on a large training set. You can prove mathematically you're not going to have a big gap from the test error. So you just train it, and you're going to succeed. Here, it's a bit slightly dodgier. It's more an intuitive argument. Yes, it seems that if a model is so good that it predicts the next word so accurately, it probably understands language. Probably. Now let's find out how good it is exactly. Now, since this is a class, I just want to get a sense of how much you've been covered. Have you covered self-attention already? Yeah. OK, then I will just skip the self-attention stuff. And you covered the transformer too, is that correct? Yeah. OK, great. Thank you. So then, transformers seem better than LSTMs right now, although who knows if that's going to be the case in the future. I want to tell you one thing about the transformer. I mean, I don't know how much you how much time you spent thinking about the transformer, but I want to say one thing about it, which is its key selling point. It's that it is simultaneously good at long-term dependencies, while also supporting parallelization over time. Like the autoregressivity makes it just fast to train. But I heard recently you've all implemented pixel CNN, so you should be familiar with those regressive models and their desirable qualities. OK, anyway, so then I can just fully skip the stuff about the transformer, and just to tell you that the core idea is just take a really big transformer and see what happens. It's a big, powerful model. It's going to predict the next word pretty well. So maybe it will understand language. That's the whole theory. This one paragraph is the whole theory. If a medium-sized transformer is a good model, then maybe a big transformer is going to be a really good model, and a huge transformer is going to be a great model. And this is the conventional deep learning logic, which, I mean, generally held so far. So now I want to tell you about some of the previous work. So one thing I'm curious about, have you covered unsupervised learning in language yet or not yet? Like things like BERT and Elmo.
Not in a lot of detail.
Well, but you've heard of these key results. So then you've heard of Elmo, you've heard of UML fit. So okay, I'll just write something. So I'll write the history. So there is Dai and Le from 2015. So they showed some very favorable pre-training properties with language modeling. Then there was Elmo from the Allen Institute. Then there was UML fit. Then there was GPT-1. Then there was BERT. Then there was GPT-2. So it sounds like you've heard of all of these except this one. Is that correct? OK, I'm getting some faint nods. I'll take it as a yes. So there is only one other result, which another result I want to highlight, which I did not list in this sequence of results. It's also the sentiment neuron, which now is obvious, the same kind of result. You train a big LSTM on Amazon reviews, and then you get a sentiment neuron, which makes sense because knowledge of sentiment is useful for predicting an Amazon review. But anyway, it sounds like you're familiar with all this work. I'll just directly jump. In this case, I'll directly jump towards discussing some of the details of the GPT-2. And basically, it's a 48-layer transformer with 1.5 billion parameters. And we had a context of size 1024. And we trained it on web text, which is a high variety corpus. And the total training compute was 100 volts for a week equivalent. Sorry. And we varied the size of the model to see how smaller models versus better models perform. And these are the sizes. We went from 100 million parameter model to 1,000 million, 1.5 billion parameter models. And they're reasonably deep, 48 self-attention layers, which is also cool. And I'll start with some of the more striking results, which is that if you take this model and you just apply it, so you take the model, you freeze the weights, you don't fine-tune it anymore, and you apply it to lots of different language modeling tasks, you get nice, sizable improvements over state of the art. For example, things like NVIC 8, Text 8, you get state of the art. Oh, Pen Tree Bank, I believe you get state of the art also without fine-tuning. So that's the cool thing. You got this big model, you pre-train it on a high variety corpus, and then you achieve state of the art in lots of language modeling tasks. You also achieve state of the art on the Lambda task. You get a big jump, biggish jump with the zero shot setting, and quite a bit more with fine-tuning. But the main thing is there you want to predict the last word in sentences which are hard to predict for language models. So you got long sentences, language models can predict the last word. This thing does better than the previous best. Vinograd schema, again, without fine-tuning, we get a big boost from 63% to 70%. And I'll show you what the Vinograd schema is. Actually, how many of you know what the Vinograd schema task is? Raise your hand if you know what it is. OK, not many. Then I will tell you what it is. So do you see the first sentence over there? The trophy doesn't fit into the brown suitcase because it is too large. And you can determine, using your extensive world knowledge, that the word it corresponds to the trophy. The trophy is too large, so it doesn't fit into the suitcase. But the other sentence says, the trophy doesn't fit into the brown suitcase because it is too small. Well, in this case, the thing which is too small is the suitcase. And the point of this sentence is that in order to figure out what does it refer to, you need to know something about the world. Because syntactically, both of these two sentences are identical. You replace too large with too small. And large and small, those two words, if you, let's say, did some kind of unsupervised word embeddings, like word to vec, large and small would have similar embeddings. So, despite this, the big language model succeeds in doing a good job on the Vinograd schema. And the way you test it is that you would replace the word it with one of the candidate words and compute the probability of the sentence. And that would give you what the model thinks about the whole sentence in conjunction with this word. Then you plug in the other word, you get the other log prob. The difference tells you the correct answer and the confidence the model has in it. So that's Vinograd schemas. That's cool. Let's proceed. Another really cool result, which I like, is open domain question answering. First, I will caveat by saying that this is one of those tasks where our performance is quite a bit worse than state of the art. So let me describe to you the task first. The task is you just have a question, like for example, who wrote the book The Origin of Species? ? And you want to get an answer. And the answer is totally unrestricted. There are no constraints of any kind about what the answer should be. You just write any text. And we just give a sentence to a model, and it writes something. And I will say two things. I will say that the performance right now is very modest. It's quite a bit smaller. It's quite a bit worse than the best open domain QA systems, which do information retrieval of some kind. Yes?
Does it have a choose or not?
No choice. It just has to generate the answer in one go.
How does it know the number of words necessary?
So that's a good question. I don't know exactly how we determine the number of words, but it's probably something sensible until like the full stop or something like this. What you see is that as you make the model larger, the model learns more facts about the world and it gets better at answering questions. It's still nowhere near as good as systems which do information retrieval and therefore don't need to memorize all possible facts. And I want to show you some of the answers that it answers, which are cool. So for example, it knows things like, what is the name given to the common currency given to the common currency to the European Union? Question mark. So that's what exactly the way the question is reads. And the answer is euro. And the model outputs that correctly. Now here's an example where the model outputs something incorrectly but confidently. Who played John Connor in the original Terminator? Question mark. Arnold Schwarzenegger. But it's not quite right. Arnold Schwarzenegger did not play John Connor. Who is regarded as the founder of psychoanalysis? Question mark. Sigmund Freud. What is the most common blood type in Sweden? Question mark. A. Apparently that's incorrect. Okay. But the point is, it knows, it understands that it's being asked a question, and it answers the questions, sometimes sensibly. And encouragingly, as you make the model bigger, it becomes larger because it uses its capacity to memorize facts, most likely. This is the theory. I also want to give you a cool example about reading comprehension. Oh yes, the question. What's web text. This is basically a collection of, I believe, so we download a large number of websites which were linked to from Reddit and from posts which had at least 3 upvotes. And that formed the basis of the data. And there's all kinds of crazy data in those websites.
Is there any fine-tuning?
All the results I'm describing right now are with no fine-tuning whatsoever. Obviously, things will improve with fine-tuning. I want to show you another cool result on reading comprehension. I don't spend time reading those 2 paragraphs, but I will tell. But instead, here's what you need to know. So in the reading comprehension data set, you have some text, in this case the 2 paragraphs, and then you have a question, and you need to answer that question. Now, how do you induce a language model to answer a question about a couple of paragraphs? Well, because the data set had about 10 question-answer pairs per piece of text, what we did is that we took the text and then we appended to it question answer, question answer, question answer. So, in other words, the model was given this whole thing as context, including the question as well. So you basically prime it into getting into this question answering mode. And you give it this question, and the important thing to know is the question says, did they climb any mountains? The humans say acceptable answers are unknown or yes. The model says Everest, and Everest happens to be the correct answer. So it is cool to see when it does these things in open-ended generation without fine-tuning. So this is all quite encouraging. And again, not again, but actually yes again, in reading comprehension there is a clear trend where bigger models perform better, and you can clearly see where the model stands relative to the previous results, both state-of-the-art and human-level performance. Yes?
So in that graph, it seems like there's like a decaying payoff. Do you like across the test, do you see that like the model, as you increase the model size, like the results get that much better, or the payoff kind of decreases?
So here is the curve for open domain question answering. So the curve is kind of different shape. Now that said, it's important that the x-axis is logarithmic.
Oh, I see.
But because the model operates in open-ended generation regime, the evaluation metrics are disadvantageous to it. Let's look at another example. And yes.
Do you know what sequence-to-sequence means in this evaluation?
I think it's I don't. My guess is probably an LSTM without attention. It would be my guess. Maybe with attention.
Quick question. So did we generate the Q&A on the previous slide? About this data?
No. So this is every training and test case consists of a bunch of text and a bunch of question answer pairs you need to be evaluated on.
But you said that you got the data from Reddit.
Oh,
The question is,
so the training data came from Reddit, but not the test data. So you have all these, so kind of you have like, I'll just draw a diagram. Maybe I can draw it here. So you got Reddit, and Reddit has links to lots of different websites. And this is the data set. And then you got, you know how in NLP you have this huge number of data sets which measure like specific aspects of natural language understanding. And these data sets are also small. So supervised learning struggles. Because you have a data set like this, for example, you'll have maybe 50 or 100,000 of pretty complicated input-output pairs. And I think it's just too hard to train it from scratch. And so that's what we are seeing. We train only on this. We train on this, but we test on the various tasks like this one.
so in your training data set, there is no question answers like that.
Not like that, correct. We did do an analysis. You know, because we had a new training set, we did an analysis of, is there a possibility that that by chance there is some overlap between the training data and our data? And in some cases we found small overlaps, but amusingly it was still smaller than the overlaps between the test data and the training data for the given task. But anyway, in this case it's cool because you see the model gets to see some text, then it gets to see some question-answer pairs, and then it figures out that it needs to continue in a question-answer type regime format. So that is all. That is cool. And now, oh yes?
Oh, another question. Like, was it sensitive to how many like question answer pairs you saw? You showed it beforehand.
So more is, well, we just showed all of them. If you don't show it any question answer pairs, it might not realize that you wanted to answer the question, if you see what I mean.
Yeah.
Because it operates in patterns and it wants to see a pattern to get going. I'll show you another examples where the patterns matter. So we tried to make the model, when creating the data set, we wanted to train on web pages consisting of English only. But by chance, our cleaning procedure wasn't sufficiently thorough, and some web pages that had English and some other tasks have leaked into the data set. And it turns out that the model can do some non-negligible translation from English to French. Let's see, where is it? Yeah. So our English to French translation by no means competitive state of the art or anything like this. But it's notable that it just works, and we didn't try to make it translate English to French. And I just want to show you how you prime it into translating English to French. You just take random training sentences, and you just do sentence in French equals sentence in English, sentence in French equals sentence in English, and you include a few dozen, maybe 7 of them, and then you have sentence in French equals sentence in English. Here we are bottlenecked by the size of the context. We have a context of 1024, and so all this training context needs to fit into 1024. And that was the reason why we used a particular number and not some other number. And if you do that, you get translation, whose performance is shown right here. And obviously we are it's not great. 12 blue points is not high, but it is still an amusing result. It's not something one would expect. I also want to show you summarization, which I think is cool. To induce a model to summarize, what you need to do is you take your sentence, you take your paragraph or document, then you append TLDR, and then you generate. And I just want to go over the numbers, because the numbers you can, we want the part, so this summarization is not as good as state of the art. But the part that's cool is that if you don't write the TLDR, you get a performance of 15.3, whatever that performance is. You get a performance score of 15.3. If you do add TL, so basically without TLDR, you just give it the paragraph, and then you ask it to continue generating. But if you add TLDR, you get quite a nice boost in performance, which suggests that it correct, or at least it has some reasonable understanding of what TLDR means. And in this case, in summarization, the curve that shows bigger models to perform better is not as strong. Here we get a flat when we go from 762 to 1.5 gigabyte billion parameters. Performance does not increase anymore. It's not clear why. I suspect that if we increase the model more, perhaps performance would increase, because it increases so consistently everywhere else. Yes?
Two questions. The first one is, if instead of using specifically the word TLDR, if you were to use some other phrase like to summarize or in summary, or this is another way of saying it.
It's a great question. Maybe it would work. It's hard to know what a model like this can and can't do. And again, the other thing to keep in mind is that it looks like maybe billion per billion and a half parameters is so big. Actually, no, it's really small, because there's so many random facts in text, so much stuff's going on. What can you learn with a billion and a half parameters? So that's the summarization example, and the translation also. And again, I want to emphasize that all these results were obtained without any fine-tuning whatsoever. There's just no fine-tuning. Obviously, if you fine-tune, results will get better. OK, so now I want to read to you a segment from my favorite sample of all times generated by the model. Now, the sample is high quality, but I want to give you two important caveats to keep in mind. First is that it took us many tries before we produced the sample. And second, in other words, we would generate a sample, look at the results, say, well, don't like it, let's try again. And we tried maybe a few tens of times, maybe 25, something of this order. The second thing we've done is that we do two tricks to improve the quality of our samples and to increase their coherence. First is we reduce the temperature of the distribution of the next word. That's the first trick. The second trick is that you truncate the distribution to assign positive probability only to the k most likely words that it assigns probability to. And if you use one of those tricks, or even both of those tricks together, you can get a nice increase in sample quality, but it will still be obviously, you will sacrifice variety. However, when you condition on a context, variety is less important. What matters is that what you generate is related to the things that you the context you gave it earlier. So I'll just read you a few sentences of this greatest sample of all time. The context is, recycling is good for the world. No, you could not be more wrong. 2 exclamation marks. Now, from this point, the model will make its case why recycling is not good for the world. Recycling is not good for the world. It is bad for the environment. It is bad for our health. And it is bad for our economy. I'm not kidding. Recycling is not good for the environment. It is destructive to the earth, and it is a major contributor to global warming. Recycling is not good for our health. It contributes to obesity and diseases like heart disease and cancer. Recycling is bad for our economy. It increases the cost of a product and in turn the price of everything that is made with this product. So the first few sentences are pretty coherent. If you keep reading this sample, you will find an incoherence, which is pretty clear. It says something that you would never say. But it's pretty cool that it could go this far and make such a coherent case for why recycling is bad. I also want to show you another example, this time from Reddit itself, from RML, where, so we released the small model, but we did not release the large model. So people on RML have taken the small model and just started playing with it. And I want to give you this example that they used, which I think is really convincing. So the context to the model is US stocks closed flat on Thursday as a solid rally faded on concerns about US-China trade talks. Markets came under pressure after Bloomberg News reported that some US officials fear China is walking back on its trade pledges. Investors will turn their attention on Wednesday to the conclusion of the Federal Reserve's two-day meeting and press conference from Fed Chief Jerome Powell. Now here's what the model is going to output. The Fed is expected to decide on March 1st whether to extend the central bank's policy limit until June. In light of the recent Fed actions in recent months, the US Federal Reserve should look at more ways it can mitigate long-term volatility. The US could also consider moving into additional buyback mechanism if it sees it unable to meet its fiscal targets like those agreed to by the Japanese government. In view of the uncertainty surrounding, so here's a mistake, an obvious mistake. In view of the uncertainty, so it repeats uncertainty twice, surrounding the future of the Fed policy, it is important that we try to maintain long-term bond yields over a longer period of time to ensure sustainable growth scenario, says Robert Vickers, chief market strategist at Credit Suisse. And someone commented on Reddit saying, I can see how GPT-2 could be maliciously used to generate believable fake news. And I want to finish my presentation by talking briefly about the partial release. And the high level is really this. Machine learning is getting more powerful and impactful, which means that you will have more amazing applications. But because it's powerful, it means that you'll also have applications you don't like, malicious applications. And right now, there exists no norms for responsible disclosure. And it is the case that you can always release something later, but you can't unrelease something if you change your mind. And all those issues about releasing something like the GPT will become a lot more severe in the future when machine learning models will become more powerful. And this concludes my presentation. So thank you very much for your attention. And I have a bit of time for questions. Yes?
How many more parameters do you think it'll take to pass a Turing test? Could you repeat the question?
Yeah, the question is how many more parameters until it passes the Turing test? Probably a fair bit more. There's only one way to find out. Yes?
So in the beginning, we were talking about how scaling up networks seems to make things improve a lot. So kind of as students, how would you recommend we kind of get into this process, considering that we don't usually have access to the same amount of compute or the same amount of resources as organizations are looking to do?
I think it's a, so if your so the question is, how could students get access to a lot of compute? And I think the answer is that it's just hard. I don't think that, get internships and jobs at places with a lot of compute, basically. I think that's one thing, and the other thing is that, with not having a lot of compute, you're naturally pushed to do research which can be done without as much compute. And I think there is lots of really good research to be done there as well. But there are things you just won't be able to do if you don't have the really big cluster. Yeah?
So we saw that at test time, the model could do some amount of pattern recognition. Because that's basically how it was primed to do the task.
Mm-hmm.
What kind of incentives would it have in training time? Like when it's just trying to predict the next word, what kind of data in the training set would sort of incentivize it to learn to do pattern recognition?
Well, if your training set consists of lots of texts with lots of repetition and lots of lists and all kinds of things, then the model will be exposed to lots of lists and lots of tabular data and all this stuff. So then when you give it a pattern, it's not going to be a totally radically new pattern. Like if you give it a complicated new pattern that involves some kind of prime numbers, it will not figure that out, probably. But if you give it a pattern which consists of, you've got a bunch of comma-separated objects, so you've got a bunch of short sentences, it knows from past experience that usually those are thematically related. And I think that's how it does it. But being specific about this is just difficult. Like, how can I know why it does one thing or another? Yes?
You referred to self-attention as a neural dictionary, and making a model with 1.5 billion parameters is like making a really big dictionary. Do you have any idea, like analytically, how large of a neural dictionary do we need to condense down like the English language? And like, does that maybe tell us how long we need to make these models? Because we saw diminishing returns already, going from like 100 million to 1.5 billion.
I mean, I think that right now the true answer is that it's hard to be sure. Condensing the English language, but what do you mean by the English language? Do you mean the internet? Do you mean, like Wikipedia? I think that question needs to be answered first. And the second issue is that I'd say one of the possible fundamental weaknesses of this work, I feel, could be, and I'm not sure, but I think it could be that this model doesn't have the ability to decide that it doesn't want to model something. It just tries to model everything. It tries to predict every single word in the data set. Whereas humans, you don't try to read every single book in the library. You're very selective about the books you're trying to read, and you pick the books which are most advantageous to you, which are most beneficial for you to read. And I think that if we have models which do that, we will find that we can achieve far more with the same amount of compute. But if the question is how big of a model do you need in order to adequately compress something which will feel like the English language, I feel like probably some unknown number of orders of magnitude larger. Yes?
How generated text is similar to other text that you have in the training data? Is it very similar, or could you compare, for instance, the last two examples that you collected? Would it be very similar to other texts around the same topic?
It's a great question. So I think the question, it's not an easy question to answer. What do you mean exactly by, what do we mean exactly by similar text? So we looked for 10-gram and 8-gram matches, and we didn't find them. But so what, you could say? Well, maybe it is good at synonyms, but maybe the high-level meaning is still preserved. But answering that question in a way that you feel like is satisfactory, I don't think there is a satisfying, well-established answer. If the n-gram matches don't happen, then what? So I feel, in other words, I think that it's just not an easy question to answer. Beyond beyond doing the 10-gram match verification or 8-gram match verification, and concluding that it's not there. Yeah.
There are some ways to summarize the text. It would be possible to compare the summaries and see how similar they are.
Well, I mean, you'd need, when you summarize the text, okay, so there are two things, right? The summarized text is similar to a context paragraph or context document, as opposed, and it would be, and so then is the concern that something similar to the context document has already occurred in the training set? Is that the question, the issue? I'm not sure I understand. Yeah, well, I can say that they are not identical, but I think it's hard. If there is some topical similarity, I don't know. But then also, if you just train on such a huge variety training set, then you're kind of close to everything. Maybe it's not so bad. Yeah?
So how much data augmentation was involved? Like you got the data from Reddit, and then how much data engineering was involved?
A modest amount. I think some data cleanup took place. We actually collected links from Reddit to web pages and just got their HTML. And also another thing I want to point out, it's a very minor detail, but I think it's somewhat nice, is that the model is essentially a character level model. It's a byte pair encoding model, which means that it can assign log probability to every sequence of tokens. So you don't worry about vocabulary. Once you got your byte pair encoding, you can throw any text whatsoever at the model without thinking. And this fact makes the data engineering a lot simpler. a lot of the data engineering in the old days of NLP, of it like at least maybe 2 years ago, the old days, you had to do work of dealing with vocabularies and stuff, and now you just don't have to do that. Yes?
Did you ever try it on something like autocorrecting?
Autocorrecting, no.
Do you think it would like work well there?
Probably. Just need to figure out how to formulate a task. It's not, or maybe you create a small training set and then fine tune on that. There's every reason to believe it should succeed. Yes?
Can you count some other data types, like speech or images?
I mean, I think, yeah, those are great questions. I think that they will need, these things are really worthy of trying. I think language has the advantage that the entropy of language is the most condensed, and the entropy of language is very semantic. So when you try to compress it, you get to focus on the high level pretty early on. Whereas images and videos, even more so, they have a lot of actual noise and a lot of boring low level stuff. So the model will not focus on the high level early on. Actually, let me give you this diagram. I think this may be an important cartoon diagram that might be true. There is some reason to believe. So if you think about your data set as a blob of entropy, and you were to partition the entropy in terms of like low level, I'm just going to do a simple partitioning, low level and high level, where low level is the stuff you don't really care about, and high level is the stuff you do care about, then it's probably the case that the low level is most of the entropy, and the high level is a tiny fraction of the entropy. And these likelihood-based generative models really they really enjoy modeling the low-level entropy. So they love to spend their capacity on the boring stuff. And I can give you specific examples of how it plays out in language. With our earlier work of the sentiment neuron, we've seen that when you train an LSTM with 500 cells, you do not get a sentiment neuron. But when you give it 3,000 cells, let's say, you do get a sentiment neuron. And why is that? Well, the small LSTM, when it tries to predict the next character, it struggles with the spellings of words and basic syntax, and it's confused by that, and it just tries to do a good job there. And if it doesn't do a good job with the spellings of words, then why should it even think about sentiment? There's no point. Then you make it large enough, it gets good at spellings. Okay, it's got the vocabulary, it got the syntax. Now it can say, okay, I'm noticing this other pattern. The same holds true with modeling images. But when you model images, the ratio of useful entropy to not useful entropy is going to be even less favorable. And by the way, all this stuff, it's kind of, I think it might be true, but it's not like I have very strong empirical evidence. But I think it's probably true. But my point is, for this stuff, for modeling the pixels to work well on images, for unsupervised learning, we're just going to need to have larger models, is what I believe. And I think all kinds of tricks to reduce the size of the model needed will be very helpful. And I think that's it. I'll wrap up here. Thank you very much for your attention.